So how was your exam? Allah Gupta.
Sir, you called me, sir?
Yes. How was your exam?
Sir, it was good, sir.
So have you attempt all questions or not?
Yeah, I was able to attempt, sir.
Okay, that's fine. Okay, so let's share. I'm sharing my screen. So tell me if my screen is visible or not. Anyone? Okay. So we have seen about the diodes and we have started some part of BJT, that is the bipolar junction transistor. One topic which is also very important is Zener diode. Okay. So in today's lecture, we will see first Zener diode and then we will go on that same topic, that is BJT. So that is a Zener diode, and we know the normal diodes, that is the PN junction diodes. PN junction diode that we know is what? The combination of P and N type semiconductors. Sorry. Right. So this is P and N type. This is P portion and this is the N portion of the PN junction diode, right? And we have seen the characteristic also. So you know the characteristic in the forward bias direction is continuously increasing after a threshold if it is 0.2, 0.7 according to the material used. In the reverse bias, very less current you will get, and in forward, this is in the reverse bias, and this is in the forward bias. In the forward bias, the current value will be in milliamperes, and in the reverse bias, it is in the nanoamperes that we know, right? That means in the reverse bias, you will get a very less current only. Now, if you increase the reverse bias voltage, this is voltage and this is the current, IV characteristic. If you increase this voltage, what will happen? After certain break in voltage, there will be a sudden rise in the current. That is because of the breakdown. And I will explain the breakdown procedure also, why it happens. So if you increase the reverse bias voltage after a certain breakdown voltage, there will be an abrupt increase in the current in the case of reverse bias. But in the case of PN junction diode, it comes at very last, means if you increase up to suppose 40 volts, then only you will get this breakdown. Okay, and we generally don't want this condition. But in Zener diode, it comes much earlier. If you consider a Zener diode, in case of Zener diode, what is the difference between the PN and Zener in construction? In PN junction diode, we use moderate doped semiconductor. Moderate doped semiconductors. In case of a PN junction diode, right? If I consider a Zener diode, we are taking the highly doped PN junctions, PN and type semiconductor, highly doped. Because of this doping, because of high doping, even if you increase a slight increase in the reverse bias voltage, there is an abrupt increase in the current. So if I draw a Zener diode, okay, so in the forward bias characteristic, in the case of forward bias, it will be similar to that of normal PN junction. You will get the current in milliamperes. But what will happen if you increase in the reverse bias voltage? Okay, if you increase a reverse bias voltage, what will happen? After a certain voltage, that is called as the breakdown voltage, there is an abrupt increase in the current. And why this is happening and everything, just I gave you the overview. Now we will go in detail. Why we are going for the Zener diode? Because in the case of Zener diode, with a slight increase in the reverse bias voltage, there will be a breakdown and you will get the current in the reverse biased also. Okay. Now let's start with a theory. What is the Zener diode, right? So understand this concept. Why we are using this Zener diode? Because in the normal PN junction diode, the breakdown will happen after a large reverse bias voltage, whereas in case of Zener diode, it comes much earlier. You can assume this is 10 volt. Around a reverse bias 10 volt, you will get the breakdown. And why this is happening? There is a difference in the doping. In case of PN junction, normal PN junction diodes, in case of normal PN junction diode, there will be a moderate doping, very less doping is there. But in case of Zener diode, you have a highly doped P and N type semiconductor. Okay, so now we will go in detail step by step. So here the PN junction with high doping, we have, in case of Zener diode, we have a highly doped P and N type semiconductors, and its doping is around 1:10⁻³ You know what is doping, right? What is doping? Anyone? What is doping?
Addition of impurity.
Yes. Yes. So here we have to highly dope the P and N type semiconductor. Both P and N. You have to take both the materials with highly doped material you have to take. This Zener diode is also called as breakdown diode, because it's actually used for this breakdown characteristic only. Okay, and it can be also used for a voltage regulator. So Zener diode can be used as voltage regulator. So because of this characteristic, by which we can use the Zener diode as a voltage regulator, we use this Zener diode. And second thing is what? The cut-in voltage. Cut-in voltage means a threshold voltage. If you are using, cut-in voltage will be 0.7 if you consider silicon, right? This is in the case of forward bias. In the reverse bias, it's around 10 volt generally we are using. And then if we see the numerical, generally they give the values in 10 volt, 8 volt like that. I'm talking about the reverse breakdown voltage. In case of reverse bias, breakdown voltage is around 10 volt. It's around, that means they will give in the numerical what value you have to take. Okay. Now question is why it's happening. If you make a normal P and N type conductor, this is a P type and this is N type. It's also a PN junction only, but here we are having the highly doped P and N type semiconductor, right? And as you know, if you want to connect in the forward bias direction, the P will be connected to positive and will be connected to negative, right? There is an immobile ions are there, right? If you apply positive here and negative here, what will happen? And in the P plus, which carrier will be in majority, holes or electron? Anyone? Which?
Electrons, sir.
In P plus, it will be holes, okay? And in N plus, it will be electrons. So what will happen? This positive terminal of the battery will attract the holes like this. Here also electron will sorry, positive, this ripple, right? Because it's hole, so what will happen? It will repel because this is positive and this is also positive. Positive to positive, what it will do? It will repel each other. And similarly, this is negative and electron is also having the negative charge, so that also repel. So what will happen? It will reduce the junction width and thereby the electrons and holes can jump from this junction and the conduction will happen. But of course, as you know, there will be some barrier potential. Okay, it's around 0.7 or 0.2 for the case of normal PN junction, right? It is same for the Zener diode also. It will be same in case of forward bias. So that means the behavior of Zener diode is same as that of PN junction diode in case of forward biased. Now, if I say what will happen if you are connecting them in a reverse bias. So for reverse bias, what will happen? You see, here you have a P plus, here you have a N plus. Why I'm writing plus plus? Because it's a highly doped material. Right? And now what I am doing, I'm connecting in the reverse bias. So the P of the terminal will be connected to the negative and the N will be to the positive of the battery. Now what will happen here? We have a holes in the majority and the electrons here are there in majority because it's N type. The negative of the battery will, what will it will do? It will attract the holes from here. Electrons from this will also be attracted towards the boundary. Because of this, the width of the junction will increase and there will be very less chance of there will be a less chance that the carrier will jump from the junction because there is an increase in the width of the junction. So this is the case when we have increased very less, means the voltage that we applied is around suppose 3 volt, 4 volt. So there will be a very less current, you will see very less current. Now, there is a phenomenon called as Zener breakdown. Zener breakdown is a phenomena which happens down. Zener breakdown happens in the Zener only. Why? Because there is a highly doped material. We are using the highly doped material we are using, right? So what will happen when you applied a reverse bias? So what will happen? The electron after certain breakdown voltage. I'm not talking about the initial stage. Okay, I'm not talking about this voltage. After this VPR, this is called as the breakdown voltage. At this point, this is actually at some threshold. If you are increasing the reverse bias voltage after the breakdown voltage, what will happen? The electron will gain the high kinetic energy and it will break the covalent bond. So if you applied reverse bias voltage increased beyond breakdown voltage. So what will happen? The electrons will gain high kinetic energy. And what it will do? It will break the covalent bond. And they also free more electrons. And this process will continue. They also free more electron due to collision. And we have a chain reaction. So because of this chain reaction, we are getting an abrupt increase in the current. So this is the Zener breakdown. When you apply the reverse biased voltage is increased beyond the breakdown voltage, that is VBR. So what will happen? The electron will gain the high kinetic energy and break the covalent bond. And they also freeze some more electron because of collision. And this process will continue, and it's just like a chain reaction. And because of that, you are getting the abrupt increase in the current like this. So this is the case when we are using the Zener diode. But if you are using the normal PN junction, there also we are having, in case of normal PN junction diode, there also we are getting the breakdown voltage, but after certain, in case of this VBR is very high, around 40 volt. After 40 volt only you will get an abrupt increase. So the phenomena which happens in the PN junction is called as the avalanche breakdown. It's the same phenomena, breakdown, but it happens when your P and N junction are lightly or moderately doped. This is the same phenomena, just the name change. Okay. Here, if it is happening when your PN and N junction is highly doped, the same phenomena when you apply the voltage beyond a breakdown voltage, the electron will gain the kinetic energy, it will break the covalent bond, and it will release more free electron due to collision. And the process is same here in the avalanche down. Only a single change is there. We have a moderately doped PN junction diode. So if it is happening in the normal PN junction diode, the phenomena is called as avalanche breakdown. And if it is happening in the Zener diode, it's called as a Zener breakdown. So this is the basic difference. Okay. And the avalanche breakdown occurs when your PN junction is lightly or moderately doped. And the Zener breakdown happens when your diode is highly doped. Now we will see what is the procedure to solve the numerical, which is more important. Okay. So Zener diode is represented like this. We have, we can represent like Z. Okay, it's actually a Z only. Okay, like this Z. So in a normal PN, we are using this Z here. So just this is the representation of a Zener diode. Okay. In case of, as we have seen in the normal PN junction diode, if it's practical, I'm talking about the Zener diode, practical diode. Here we don't have a, we can consider ideal or practical. Okay, so let's start with normal practical diode. Okay. So when it is a forward biased like this one. Okay, and for the representation you can use like this. If it is connected to positive and this terminal is connected to negative, okay, and this is forward bias, so you can represent with a cut-in voltage V gamma, or you can say a cut-in voltage. And the Zener diode will always be manufactured with a silicon. Always. We cannot use germanium. Okay. We generally use silicon to manufacture the Zener diode. So the cut-in voltage will always be 0.7. Okay. So you know the procedure of solving the question in the normal PN junction diode. If it is forward bias, we was replacing with a cut-in voltage. Here also you have to do the same thing. There we was having germanium and silicon. Here you will have only silicon. The forward bias Zener diode is replaced by its cut-in voltage. Now, if it is a reverse bias, what will happen? Reverse bias means what? You can represent like this. And this terminal is negative, this terminal is positive. So you can, in the case of ideal diode, what we was doing? Tell me anyone, if a PN junction diode is a reverse bias. So
open circuited.
Hello. Yes.
The open circuited.
Open circuited. And in case of yes, in case of practical and ideal, it will be same in reverse bias.
Yes, sir.
Yes. Now here, In case of practical, there will be a resistance and a breakdown voltage, that is VBR. And in case of BBR, this is the breakdown voltage. That means a Zener diode will be replaced by a series connection of resistance as well as the breakdown voltage. And if it is an ideal diode, then it will be replaced like this. This is only with VBR. This Zener voltage resistance is very less. But if it is practical, you have to consider this RZ. But if it is ideal case, you can skip this one. In case of ideal, in the forward bias, what will happen? Anyone tell me? It will be a short circuited or open circuited. Tell me. This was the practical case.
Short circuited.
Yes, it will be short circuited if it is an ideal case. So for better understanding what I'm doing, I'm just start solving some numericals. Okay, so let's start.
The breakdown
You
voltage,
have-
how much we will take?
It will be specified in the numerical. If it is not there, then you can consider around 10 volt. It's around 10 volt. Okay, so if it is, it will be specified in the numerical. If it is not there, then you can consider 10. Now, question is what? Find out the output voltage, and suppose this is, and how you will know that this is a Zener diode by this its sign. If it is like this Z, then you have to consider as a Zener diode. Okay. From the next time you see the symbol of PN junction. If it is normal PN, so you will not get this thing. If it is like a Z, it's showing that it's a Zener diode. It's 40 volt, and here in the breakdown it's given. Breakdown, that is VBR is given. Suppose 10 volt. Okay. And this is silicon. Okay, silicon type of material we have used, and you have to find out the V output. So always you have to see whether your diode is forward bias and reverse bias before solving any type of diode circuit. First see that diode is forward bias or reverse bias. So please tell me whether the diode is forward bias or reverse bias.
Forward bias.
Forward biased. Forward.
It is forward biased. Okay. And if it is not specified, always consider as a practical. If it is specified that it's ideal, then only you have to consider ideal. Otherwise, in all the cases, you have to consider practical diode only. Okay, so it's very important thing. You have to consider always practical if it is not specified. Okay. Now, as you know, in the forward bias, you can replace this diode with a cut-in voltage. That means if it is suppose 30, okay, 3K, suppose it's 3K, and this is 40 volts. So I can replace this one as a voltage across this one, and this voltage is what? In the forward bias, as I told you, the germanium will be manufactured with only silicon, so the cut-in voltage will be what? Anyone?
0.7.
0.7. Okay, and you can find out the value of V out. Tell me the value of V out. Anyone tell me the value of V out?
So can you repeat? You are not audible.
What will be the V output, the output voltage?
233.3.
See, V output we have to find out across this diode, and this diode
Okay,
is
sir.
so it will
Sir, I thought
0.7
it's
volt.
I you are asking.
okay. It will be 0.7, right? Now I'm drawing one new circuit, and you have to tell me the V output voltage. Question number 2. for example, you have a resistance like this and one diode, one more diode. Suppose this is 40 volt, this is suppose 3K, and you have to find out the V output. And I'm specifying that it's manufactured with silicon. This is also silicon. Tell me the V output voltage.
Sir, both are zero diodes.
No, one is PN junction diode. So for this, you have to see the symbol. First one is the normal PN diode, another one is a Zener diode.
And it is practical, sir.
All is practical. If it is not specified, it's ideal, then you have to consider as a practical only.
So 1.4 volt.
Yes, it's 1.4. Because both the diodes are forward biased, right? So you can replace like this. And both are silicon, so the cut-in voltage will be 0.7. And for germanium, you have to consider it's manufactured with silicon only. Okay, so always you have to consider as 0.7. For the PN also, they can specify it's a germanium. So if it is germanium, then you can consider as 0.2. If it is silicon, then you can consider 0.7. And just you have to add these two terms. As I have taken silicon, so it will be 0.7 and you will get 1.4 volts across these diodes. Understand? So now you see the third question. And K, suppose here we have 40 volts. And you have to find out the V out. Tell me the value of V out. First, tell me whether the diode is forward biased or reverse biased.
Reverse bias.
Is a reverse biased, right? As I told you, if it is reverse biased, in the practical scenario, it will be replaced as what? A resistance. You can see here, if it is a practical scenario, it will be replaced by what? By a resistance and the VPR, right? So I can replace it with a
So,
resistance. Yes.
so you have not put the positive and negative sign near the 40 volt nozzle. So how will you take it as reverse bias?
Yes, positive, negative, positive. Terminal
Okay, sir.
positive. So here it's 3K, okay, and here as this is a reverse bias, so the sign will be like a voltage like this, and this is positive, this is negative 40 volts, and across this you have to find out the V output, and this value will be equals to VBR, okay, and this VBR, if it is not specified, you have to consider as 10 volt. Generally, they will provide you this value. They will give VBR, suppose 12 volt for they have given, so you can consider 12 volt. If they have not specified, you can consider as 10 volt. And this resistance value is very small, and they will specify that the reverse breakdown voltage resistance RB is around suppose 100 ohm. But if they not give, you can assume this is negligible. If they not specify the value of resistance, we can consider as negligible. If they specify, you have to write down here 100 volt like that, 100 ohm like that. Okay, understand? So we have seen how the diode will behave if it is in the forward bias, if it is in the reverse bias. Right?
Sir, I have a doubt, sir.
Yes.
So why did we take opposite voltage? I mean VBR as?
VP. Okay, sign you are saying, right?
Yes, sir.
VBR is a negative voltage because the reverse biased, right? So VBR is actually the negative voltage only. If you draw, this is the reverse voltage. Okay. So either you can change the sign or you can change. You can use minus sign, minus 10.
Okay.
It's up to you. It's up to you whether you are using minus 10 or you are changing the sign. Either of it you have to do. Either you take -10 or you can consider as a change of the battery sign. Okay.
Yes, sir. Got it, sir.
Okay. So let's see the next topic.
Sir, could you repeat it, sir, once again, sir?
Yes, in the reverse bias, as you know, in the forward bias, we was having the voltage here and the current here, right? And in this direction, if you see, it's a reverse bias voltage will be in -1, right? So either you can take as a -10 or like this, -10 or -20, whatever is there. Either you change the battery sign. So it's up to you whether you are changing the battery sign or you're changing the, you are using the negative sign. Either of it you have to do, not both. You cannot take negative as well as change in the battery sign. Either of it you have to do.
Sir, and V out is going to be the voltage around like the
Voltage around the diode, yes. Voltage around
only,
the diode.
yeah, so including that 100 ohm resistance, right? So it should be
Yes,
in that
yes,
whole
yes,
branch.
yes. But if
Alright.
if it's they don't give this value, you can assume as negligible, and then the voltage will be same.
Yes, sir.
Okay, so let's, yes.
So the output for the previous one should be 12 volts.
For the previous one.
This one, sir, the reverse bias.
This one, yes, 12 volt, 12 volt.
Okay, sir.
Now one more thing. Yes, okay. So now we will move to the next topic.
Excuse me, sir.
Yes.
So can you solve some numericals on BJT circuit?
That we are going to start, right? So we have seen about the diodes. Yes, more and more thing is there in the Zener diode, how it's working as a voltage regulator. So it's just a theoretical part I am explaining in some 2 minutes. Okay. What is that meaning of a Zener diode as a voltage regulator? Zener diode as voltage regulator. So first thing is that what is the meaning of this voltage regulator? So if I am saying this is a voltage regulator, means what? It provides a stable DC voltage. It will provide a DC voltage, stable, okay? Stable DC voltage, which is independent of a load current, temperature, and a line voltage. That means if you are changing the load, even you will get the constant DC output. Even if you are changing temperature, then also you are getting the constant DC output voltage. Even if you are changing the source voltage, it's called as the line voltage or source voltage, even you are getting the constant voltage at the output. Because of this characteristic, we are saying that a Zener diode is a voltage regulator. So when we talk about the Zener diode as a voltage regulator, we should know what is the meaning of voltage regulator. Voltage regulator means what? Which provides a stable DC voltage, which is independent of load current, temperature, AC line voltage variation. Okay. So if you are getting the constant output here, called as the voltage regulator. Now, in our syllabus, we have a line regulation and the load regulation. Line regulation and load regulation. Two types of things we have to understand from the Zener diode as a voltage regulator. So what is the meaning of line regulation? Line means what? A input line. That means a input source voltage. Source voltage. That means if you are changing the source voltage, okay, let's see in detail. What is the line regulation? Line regulation. Line regulation means what? If you are changing your source voltage, even you are getting the constant DC output, it's called as the line regulation. So here I am using the diode. Here we have source voltage, that is Vs. This is the series resistance I am representing with RS, and here you have a load resistance RL. Okay, what I am saying, if you are changing the source voltage, that is VS, okay, and you are getting the output across this as a constant one, okay, that means it will be work in a reverse bias only. So whenever you say it's a regulator, it will always be work in the reverse bias because we have to come in the breakdown. What will happen in the breakdown if you are increasing the reverse bias voltage? The sudden abrupt change will do what? It will give a constant voltage, right? This VBR. Okay, if you rotate this graph, what you see, it's like you are increasing the voltage up to here VBR, right? And then you are getting the abrupt increase in the current. So it's the constant one. The voltage is constant, right? Voltage is constant. So that means what? As the voltage is constant across the load, even if you are increasing the source voltage, this Zener diode is working as a voltage regulator. So in this type of regulation, a series resistance, load resistance are fixed. So this is fixed, RL is fixed, and RS is fixed. So I can write down here, RS and RL are fixed. Whereas you are changing the value of VS, either you are increasing or decreasing, right? So in that case, it will maintain the above minimum value, and the percentage line regulation you can consider, you can find out is percentage line regulation is the change in the V out and change in Vn in 100 multiplied by 100. So if anyone asks what is the percentage line regulation, if you are changing the input voltage, because we are changing the V source, right? Source voltage. So if you are changing the source voltage, what is the change in the output across this one? That is the output voltage multiplied by 100 will give us the line regulation. Okay, so what we got from here, actually we have two type of regulation. One is the line regulation and another one is load regulation. Line regulation means what? If you are changing your input source voltage, even though your output is constant, it will be in the reverse bias only, because the Zener diode will work as a voltage regulator in a reverse bias. So after breakdown, what will happen? Your voltage will be constant, and you can find out the percentage line regulation by this formula. That is the percent change in the V out divided by change in the V in. So it's actually it's similar to like this one. You will get the. You can also have a lab experiment based on this. I think you have solved this problem. Okay, here you was getting, if you're increasing the input voltage, that is V in, you will get the V output like this. After certain time, it will be constant. Right? And you was you have find out this change in the line regulation. This is called as the percentage line regulation. Now, what is the meaning of load regulation? Load. In the load regulations, circuit will be same, okay, like this. And as we have to use in the reverse bias, because this Zener diode will work in the as a voltage regulator in the reverse bias only. And here we have a resistance. Here you have to consider VS is constant, RS is constant, but this load resistance is varying. It means even if you are varying your load resistance, the voltage across the diode will remain same. Okay, so the formula to find out the load regulation is V at no load minus V at full load divided by V at full load into 100. Now, what is the meaning of this no load? If you are not connecting this resistance, load resistance, if you are not considering this, or you are first, no load means what? No load, no load. No load, when you remove this load resistance and you are finding the voltage across the Zener diode, is called as no load voltage. And when you connected this load resistance, full load means full, the highest value. And then you find out the voltage across this general diode. And then you have to find out the load regulation by this part. Okay. So this is the way to find to know that this general diode can work as a voltage regulator. Voltage regulator means you will get the constant DC output at when even if you are changing the line voltage or also the load. Right. So this is about the general diode. Okay, so just an overview that we have seen for the.
Sir, can you show the formula again?
Yes, yes.
FL is basically the full load, and
Full
where
load
should
means
we?
what? Yes, yes. See, no load means what? First, you have to remove the load resistance and then find out the voltage across the diode. That is the no load condition. Full load means the highest value. Suppose it's varying from 10 to 100 ohm. You have to take the 100 ohm and then find out the voltage across this diode. Then you can find out the percentage load regulation. So they will give you direct the value of no load condition, full load condition. Then you can find out its value. Either they will give you the load. Suppose they will give RL is varying from 10 to 100 ohm. So what you have to do? You have to consider this 100 ohm and find out the value, the voltage across this diode. Okay, so that will give you the V full load. No load, no load means what? You remove this RL, remove RL and find out the V no load. Understand? Okay, let's see one more numerical. But
Sir,
if
can
you're
you
not-
show the circuit for the line regulation?
line is line.
Yes, sir, 1 minute, I'll take a screenshot.
Sir, the diode for line regulation is not Zener.
It's Zener. Always. Okay, let's see one numerical if you have any problem. See, if you have a circuit like this, suppose here I am giving the fixed value as 10 volt, for example. Okay, and this is the resistance RS. Suppose it's a constant value and which is around 100 ohm. 100 ohm. Okay, and here I am using one Zener diode like this, and this is the RL value. RL, and this is varying. Okay, so this is varying from 1 to 1000, for example. So what you have to find out what is actually varying? The RL is varying. So I am asking to find out the percentage load regulation. Percentage load regulation. So how you will find out? The first step will be what? First step is find out the V at no load. Okay, that means you remove the RL and then find out the value of this voltage. And tell me whether always will be in the reverse biased, right? So you can see it's a reverse bias condition. So in the reverse biased, as this, tell me the diode is reverse biased or forward biased?
Reverse bias.
Reverse bias. So you can replace with a breakdown voltage, right? VBR. For example, it's 10 volt, right? So what it will do, it will give like this, and this is VBR, and the value is 10 volt, right? So
Are we considering the diode as ideal?
as the resistance is not given and assume as negligible, so of course you can consider as ideal. If it is given, then you can find out its value, right? For example, I'm considering as very small, for example. So in that case, what will happen? The voltage across the diode will be 10 volt. Is it clear? So this is V no load condition. V no load will be 10 volt. Now you have to find out the V at full load. That means you have to connect this terminal that is 10 volt, then this is 100 ohm, and this is your battery, okay, and this is suppose 10 volt only, and he changed this one, okay, here it was 10 and now you consider as 12 volt, consider as 12 volt for example. So voltage will be across this one will be 10 only, okay, 10 it will give 0, that's why I'm changing, okay. So you change to 12 volt here. It's 12 volt, here also is 12 volt. This is 12 volt, this is 10 volt, and you have to connect this resistance here. Resistance, how much resistance you have to take, because the RL resistance was changing from 1 to 1000. You have to consider here what voltage, what resistance, tell me.
1000.
1000, sir.
1000 ohm, right? Now tell me the voltage across this diode. Here actually it's important to have a resistance, right? Otherwise it will again give you the 10 volt only. Of course, right? You will get the same resistance. If you are using the, if you are not using the resistance, you will get 10. In ideal case, it will be 100%, of course. So it's better you consider a 100 ohm here also, and here also 100 ohm. So that will give you the clear idea. So in that case also you find out the no load once again, because I'm considering the internal resistance, and this is also internal resistance of 100 ohm. So for both the cases, tell me the value. It's no load condition, also you tell me the value. This is 100 ohm. Tell me the value of no load in the case of no load also. You can apply a current here and use the like minus 12 plus 10 plus 200 I is equals to 0, so that you will get is 2 equals to 200 I, so I will be equals to.
Sir, V no load is 11, is it?
Okay, 11, right?
Yeah.
Okay, right. And what about this full load?
Sir, around 10.5.
Around 10.5. Okay. So if it is like that, now you can find out the load load regulation percentage load regulation, right? So it's V no load minus V full load divided by V no load, right? Tell me the percentage regulation in multiplied by 100. Sorry, divided by 3 volts. $11 minus 10.5 divided by 10.5 in 200 like this.
Sir, 4.76.
Okay, 4.76. Okay, understand? No? Actually, I was just giving you the idea how you can calculate the load regulation and the line regulation. Okay, so here in the load regulation, you have to find out the no load condition voltage, full load condition voltage, and then you can find out like this. In the line regulation, you have to actually plot it. So numerical is not possible because if you're changing the voltage, what is the change in the output voltage that you can see in the LT Spice. Okay, software. There you can change the input voltage and check what change out in the output voltage you are getting. So that's all for this today's lecture. If you have any doubt, you can ask. We will see the BJT part and the MOSFET part in the next lecture.
Thank you, sir.
Thank you. Thank you, everyone.
Thank you,
can
sir.
Thank you,
share
sir.
this PPT, please?
Yes, I will share this paper.
Sir, can we write percentage load regulation in terms of resistance?
Load regulation in terms of resistance. You try. I don't think you can because here you have to include the resistance and in no load we are assuming the load resistance is 0. Then you try once, huh?
Okay,
Try
sir.
once. And for today's lecture, I am sharing this that PPT. Okay.
Thank you.
Thank
So
you,
you
sir.
will get today's lecture notes in the meeting chat.
Thank you, sir.
Thank you, sir.